Okay, we're ready for our next talk. Daniel is going to talk about Netdevices. Thanks.
All right, thanks a lot. So this talk is about Netdevices. This work has been done by my colleague and myself. We are at Isovalent software engineers working on the kernel and also Cilium. So really the goal is the question we were asking ourselves, like how can we leverage the BPF infrastructure in the kernel and also the networking features to really achieve maximum performance for Kubernetes pods. And before I go into the kernel bits, just a really quick recap around Kubernetes and pods and what it is. So basically what you can see here is a host. A host can have one or many pods in Kubernetes. It's an orchestration system essentially, and a pod is usually defined as a network namespace, and it is connected typically to Weave devices to get traffic in and out of them. A pod can have one or many containers that are sharing this network namespace. So yeah, and CNI is basically a networking plugin which will set up various things. When a pod comes up, for example, it will set up Netdevices, assign IP addresses. It has an IPAM infrastructure to manage a pool of addresses. It will install routes. In the case of Cilium, which is a CNI, it will also set up the BPF data path, so to basically route traffic in and out. It has various features on top as well, such as policy enforcement, load balancing, bandwidth management, and so on and so forth. But I don't want to make this talk about all the different features about Cilium, but rather about performance. There was an interesting keynote last year at the SAEcon from Brandon Gregg, where he talked about computing performance and what's on the horizon. And he had a couple of predictions, and one was quite interesting when he was talking about OS performance. And the statement that he made is that given the kernel is becoming increasingly complex, the performance defaults are getting worse and worse. So he stated that it basically takes a whole US team to make the operating system perform well. And the problem is given all these performance teams, they're trying to optimize at the larger scale. Nobody's actually looking at the defaults anymore and how they can be optimized. So this was quite interesting. So yeah, in case of defaults, we were wondering given two Kubernetes nodes with pod to pod and they're connected with 100 gigabit NIC, we wanted to look at a single flow, like a single TCP stream, and we asked what's the default baseline you can get to? Where are bottlenecks? How can they be overcome? And actually, can we provide better defaults out of that? What we figure out. Why bothering with single stream performance? Well, there's first of all, it's interesting for the kernel to be able to cope with the growing NIC speeds, so 100, 200 gigabit or more. How can this be maxed out with the single stream? There are a lot of data-intensive workloads. From user and customer sides around machine learning, AI, and so on. But generally, it's also interesting to be able to free up the resources and give them to the application instead of the kernel having to block them. So the assumptions for our test is basically usually the Kubernetes worker nodes that users run, they are quite generic. They can run any kind of workloads. What we are also seeing is a large number of users typically just stick to defaults. They don't tune specifically the kernel. There's an interesting cloud-native usage report where they try to get some insights into how Kubernetes deployments usually look like. There's definitely an increasing trend to have a higher density of containers per host. So around 50 or more is expected these days, and the number of pods per node is also increasing. The question now is, okay, so a very basic compatibility setting for example, for the case of Cilium, we use if you deploy it in a basic mode, we just use the upper stack for routing and forwarding. There are various reasons why people might want to use that. For example, in case of Kubernetes, there's a component called kubeproxy, which uses NetFilter IP tables for service management, for service load balancing. Some people stick to that. Or they have custom NetFilter rules, so maybe they require to use the upper stack for that. Or just simply they, for now, just went with defaults and might look into more tuning at a later point in time. So when we try to look at the performance for that, what you can see here is on the yellow bar is the host-to-host performance for a single stream. So we got to 44 gigabit per second. But then if you do the port-to-port connectivity, it's really reduced dramatically. And so, yeah, like one of the reasons is, and I will get into this in a bit, is because the upper stack is giving false feedback to the TCP stack. One thing that we did like a year ago or so is to introduce a feature where we can, which is called BPF host routing, where we don't use the upper stack. And for BPF itself, like given we attach to physical devices, but also to Weave devices, we added a couple of new helper functions there. One is called BPF redirect peer. What this basically is doing is adding a fast switch into the network namespace for the ingress traffic. So basically, we're just instead of going the usual XMID route to the Weave devices, we can retrieve the Weave device inside the pod and just scrub the packet to remove the necessary data that we typically remove when switching network namespaces, but then also to just set the device to the device inside the pod, and then circle that around in the main receive loop without going through a per CPU backlog queue that you would normally do when you transfer data through Weave devices. And we don't need to use the upper stack because there's all the information already available in BPF context. And for the way out, we added a helper which is called BPF redirect neighbor. So that one will basically insert the packet into the neighboring subsystem of the kernel. So usually we can do a FIP lookup out of BPF. So there's a helper for this as well. And then combined with this for the resolution of neighbors, it will allow that you don't need to go to the upper stack. So, and the nice benefit you get as well with this is that the socket context for the network packet for the SKB is retained all the way to the physical device until the packet is actually sent out. And this is not the case when you normally go to the upper stack. So then the TCP stack actually thinks that once you go to the upper stack that it already left the node, but it's actually not the case. And this way it can be retained. And this is how the complete picture looks like. And if you look at the performance, it's already much better. So we were able to get almost to 40 gigabit per second under 1.5K MTU. So this was interesting. Now the question is how could we close the remaining gap? Under 8K MTU, we also did some tests, and one thing to note here is that we were able to for single TCP stream to get to 98 gigabit per second for the host-to-host case, but still the situation looks quite the same for the Weave with the BPF host routing. So there's still a small gap that we want to close here as well, and that's where we introduce a new device type as a Weave replacement. So we call this meta device because it's programmable to BPF, and you can implement various, your own business logic into this. So it's flexible, and this time, the main difference is that this also gets a fast switch on the egress side for the egress traffic, so it doesn't need to go to the per CPU backlog queue for the egress as well. So if you look at the flame graphs, so that's like the worst case scenario where we compared the Weave and the Meta device. So what you can see here on the Weave device, like on XMIT, it will basically scrub the packet data. It will enqueue the packet to a per CPU backlog queue, and then at some point there's a network's action. It will pick up the packets from the queue again, and in the worst case, it can be deferred to the kernel soft IRQ daemon, and then you see this rescheduling where you have a new stack where this is processed again. And then from the BPF side, it will reach BPF on the TC ingress on the host Weave, where we then can only forward this to the physical device to leave the node, right? And all of this can be done in one go without rescheduling through this Meta device. So it will scrub the packet, it will switch the network namespace, it will reset the device pointers, and it will then directly call the BPF program. And if the BPF program says that, based on the FIP lookup and so on, that it will forward the packet directly to the physical device, then it will avoid this rescheduling scenario. So on the right side, it's really straightforward. That's how the implementation of the driver XMIT routine looks like. So it will basically just call into BPF and then based on the verdict, push it out. It's really just 500 lines of code, so it's very simple and straightforward. I think it's just 1/5 of the Weave driver that we have right now. And the other focus that we wanted to put into is compatibility as well, so that given in Cilium we need to support multiple kernels. The ideal case would be that we don't need to change much of the BPF program and can keep it as is. And in case of XTP, we didn't want to implement it because for the Weave case, it really is very complex. It even adds multi-queue support, which you normally would not need on a virtual device. So we wanted to keep it as simple as possible and to have the flexibility that this can be added as a single or a paired device. So for the Weave replacement, it would be a paired device, but you could also do it as a single device and then implement whatever logic you would want in BPF for that. So looking at the performance, again, the TCP stream under 8K, so this is really able to reach through this approach the full 98 gigabit per second. And in terms of latency, so we did some netperf TCP/RR measurements as well, where you get the minimum, the P90, 99 latency, and so on. So this is really on par with the host. So now we were asking ourselves, so can we push this even further? So we were able to get to 98 gigabit per second, but the cost for a megabyte to transfer can this pushed even more. And there's a relatively recent kernel feature, which is called Big TCP. It landed for IPv6 only in 5.19 and was developed by Google. And the whole idea behind Big TCP is to even more aggressively aggregate for GRO and GSO. So normally the aggregation, the kernel will try basically out of the incoming packet stream, create a super packet, and then we'll push it up to the networking stack, so it only needs to be traversed once. And the limit up until that point was for 64K packets, simply because in the IP header, that's the maximum packet size that you can do. And the idea for Big TCP for IPv6 was that, well, maybe we could create a hop-by-hop header in the GRO layer and then add, and then the 16-bit packet length field can be overcome because there's a jumbogram extension in there which allows for a 32-bit field. So you can do much more aggressive aggregation. And yeah, so this is also now supported with the new Cilium release, where this will be set up for all the devices underneath automatically for IPv6. Actually, this week, there was got also merged for IPv4 now. So this will land in kernel 6.3, which is exciting. And when we looked at the performance again under Big TCP, Turns out like using the upper stack is currently broken in the kernel, so that still needs to be fixed. We will look into that. So forwarding there wouldn't work. Then with the host routing cases, so it will basically bump up the regular weave one to get this on par with the meta and also the host. So it will basically hide those glitches. The latency is still better in terms of like the short packet request response type workloads for the meta. So that's still on par with the host. So what is the remaining offender like when you run all these features together? It's basically the copying to users. So like between 60 and 70% of the cycles is really spent on copying all this data to user space. So the next question we ask ourselves actually in this experiment, so what if we combine the whole big TCP stuff with TCP zero copy? So what if we could leverage the memory map TCP? And it turns out that's currently not possible in the kernel. That's a limitation because in the GRO layer, big TCP will create a frag list, which is essentially like a list of SKBs, as a single big one that is being pushed up the stack. And TCP zero copy only works on the SKB frags. So that's like an internal, so where basically you have a single SKB and it has like the pages as read-only attached in the nonlinear section. So that currently does not work. Combining those two would probably have like really big potential. But what we now try to do is we just looked at just using the TCP zero copy to see how it looks without the big TCP. Generally speaking, it's not as straightforward to deploy because first of all, you need to rewrite your application in order to leverage memory map TCP. This can be done for RX, but also for TX or both. And it needs driver changes. And in particular, driver changes to be able to split the header from the data because the data you want to memory map to user space. Some NICs might do this with the hardware, and some others you would have to do some kind of pseudo header data split, so where you basically just copy the header into a linear section. So this is how it would look like. We tried this for 4K and 8K MTU. There's a great talk from Eric Dumaset, the TCP maintainer, in terms of what all those things you need to do in order to be able to make use of this. For example, you also need to align the TCP window scale to 12 segments so that you fill exactly those pages. And yeah, the driver support can be very different. Like we had in our lab MLX5 100 gigabit NICs, and they did not implement the header data split. So my colleague Nikolay did the POC implementation to change the driver to be able to do that, so that we could get some measurements out of this. And if you want to look into an application, like an example application, and how you can implement that, there's one in the networking self-test in the upstream tree called TCP mmap, which is useful also for the benchmarking. So you really need to align various different settings. Like for our test implementation, we used, like for MLX5, the non-striding mode, so like the legacy mode. So you need to switch that off and Eve tool first, because for the POC it was easier to do the way like the packet layout is done there. Then you need to align the MTU to either one page or 2 pages, and you need to do various other settings. Like for the course of time, I will not go into all of the details. And generally, I would think it would be useful addition to the kernel to have like a configuration framework for that, and to be able to have more drivers supporting the header data split. There's actually one in Windows kernel, turns out. So there's some documentation around there that we found while preparing for the talk. The other thing as a caveat is like the TCP zero copy the benefits might be limited if you then actually go in your application and then touch the data, because then they need to be pulled into the cache, which they would be if you would have to copy things to user. but they may not be like if you just memory map. So the applications there is mostly like on the, for example, storage side where you wouldn't have to do that. And looking at the data for 4K MTU, what we tried with the implementation, we got to 81 gigabit per second. So that's a bit limiting. Could also be that this is mostly because the implementation was a POC with lots of optimization potential that can still be there. But we looked at the 8K MTU, and there we were able to get to 98 gigabit per second. But the interesting piece here is the cost per megabyte we were able to reduce from 85 down to 27 microseconds per megabyte. So that's really significant. And yeah, because of the avoidance that you don't copy anymore. So as a summary, so we started with the default and then switched to the 8K MTU. Then we went to the host routing that we covered. Then the addition of the meta device where we can do this low latency, for ingress and egress. Then the big TCP, and that all works without changes to the application. And with that, you can already get like a 2x improvement. And then it gets even more dramatic. But it's, of course, dependent on your application for the zero copy. Some of the future directions, as I mentioned earlier, it would be useful to have like a generic header data split framework for NIC drivers that they can implement that and expose it, this setting. There's potential here as well to optimize. For example, like the header pages could be, the head page could be packed with the headers. It could get recycling, which we didn't implement here. And in future, big TCP would be interesting to combine with the zero copy so that this covers the frag list in GRO. And the other thing that is at some point on the horizon is to push the big TCP actually onto the wire as well, if the hardware supports that. And yeah. So with that, I'm done with the talk. And the prototype for the meta device is currently you can find on this branch. We are working on pushing this upstream in the coming months. And there's also the prototype public for the MLX5 header data split. And yeah, so the plan is basically to get this into upstream kernel and then also to get this integrated into Cilium for the next release. Yeah, thank you. Are there any questions?
Thanks. We already have 2 questions in the chat, so we can start with them if there are no in the room.
All right. So the first question we got was, not really a question so much as a comment, I think, which is, can we please come up with a better name than Meta for this? Just call it BPF or BPF Dev or something like that.
BPF Dev.
Yeah. The other thing was, if the perf benefit comes from calling through from inside the network namespace, can we just make VF do that instead?
I think we could, but the question is, like, I haven't looked into the how it would affect the XTP related bits. So it felt easier to do something simple and start from scratch. Like, one thing I don't really like about the Weave device is, to be honest, how complex it got with all the XTP additions, and it's not even that beneficial. And it added like multi-queue support and all of that, which was not needed at all for a virtual device. So I really wanted to have something simple and easy. So,
any more questions from the audience here? Perfect.
Thank you. I have a question about big TCP and TCP zero copy. It's in your lab. You only did benchmarks host to host, right? Because
so, but also port to port. So we tried both. Yeah.
Okay. Because do you know how it would work with the switches? Do you need special switch support for?
No. So the big TCP is only local to the node. Mm-hmm. So like the packets on the wire, they will still be your MTU size packets. It's just that the aggregation on like for the local stack is much bigger. So
Okay.
it doesn't affect anything on the wire. That's the nice thing.
Okay, and for zero copy?
I mean, like for the zero copy, you need to change definitely the MTU, which also affects the rest of your network, of course. So that's one thing that would be required for that.
Thank you.